planning on it, but if you're interested, I can go through the sum example as it would be done in PVS. It would only take a couple of minutes, I believe. So there's the
You
theory.
also have to double bracket.
What's that?
You also need to brackets around the n times n to the.
Yeah, well, you don't actually. You don't actually. But anyway, so you start off by type checking this, which is meta XTC. So Emacs is the original GUI to PVS. There's now a VS code that's been developed by NASA, so I'm not very good at it, and I don't want to screw up a demo with that. So it type checks. You see that sum is the recursive function that you were talking about. There are no ampersands or anything. There's in fact only 1 0. It's natural, it's integer, it's rational, it's real, it's the only 0 there is. Although you can define 0 to be another thing, like if you want to define group theory, you can say it's group with plus and 0. And it knows, oh, if you're talking about the group 0, the type checker knows, oh, you mean that 0 instead of the integer 0, or the number 0 actually is what it is. And then you notice there's a variable nat. That's a logical variable, not a state variable. You can't. There is no state in PVS in that sense. You can model it, of course, but there isn't. And the closed form has that n, just like you were talking about. The difference is that when you start this proof in PVS, you put the cursor near the formula you want to prove, and you do it minx PR. And I'll say no, I'll rerun that. And it closes it, basically. The sequence calculus. So this is saying that the hypotheses and the conclusions are here. And it's the conjunction of the hypotheses implies the disjunction of the conclusion is how you read that. So the natural thing to do here is induct over n. And unlike that, you don't get the linear form. There's in the background a tree. In fact, I can. So here's rather small, but there's the tree up there. So the circled one is the current goal we're working on. And that's obviously the base case. The base case is rather simple, and as you all know, grind is what you do when it's simple. And then it takes care of it. And this is the next step, the inductive step. Well, all I do there is grind again. And I'm done. Now, I won't bother to save it. But in fact, when you want to do proofs like this, I often, instead of that, do another proof. I'll try again, but no, I don't want to use. Usually I actually, for things that I think are this simple, I do induct and simplify, if I can type it. Still have to give the induction variable, and then I'm done. So that's just a quick introduction to PVS before I go into the module system of PVS, which is quite a bit more complicated. Any questions about that? Okay, then let's start the slides. Over too far to see. Okay, so PVS actually is very similar to STEC in structure, et cetera, So it consists of libraries. At the highest level, you have libraries, which are really just directories that contain PVS files. There's not, but they'll also contain, when you're finished with a proof, it generates a .prf file. So you write the interactive proof. You don't have to do this logging thing. It just generates the .prf file. It also supports multiple proofs for the same formula. So you can have a proof and it worked, but you want to kind of clean it up for making a paper or something. You can create a separate proof for the cleaned up proof. or you might want a proof for pedagogical reasons as opposed to a proof that you actually want to present.
I had a question about that actually. So I have reviewed PVS papers and I've looked at PVS sources and I see the proofs and then I don't really understand what I'm looking at. How do you present PVS proofs to people?
I'm hoping to be able to use STEC for that because right now, basically you replay the proof, kind of like I would do. So I could have started the sum and then for instance, there's a step proof command, and that starts the proof and gives you a buffer where the proof lives. The current default proof is, and that just looks like a bunch of steps indented by list. It's a parenthesized thing, so so you can follow where the indentation is to tell you what branch you're on.
But is there something that automatically does that for like the whole proof and generates you some output?
There's a couple things done that way, but it's none of them are that great, I would say. But yeah, so let's see what else. The PVS files can have multiple theories, modules, theories or data types or co-data types actually. They're essentially co-algebras. Modules may have parameters, as you'd expect. Data types and co-data types generate theories that essentially are, the data type mechanism generates induction and all these things from the constructors that you define. I can show those later if somebody's interested. And theories, of course, can import other theories. So libraries, everybody's heard of the NASA libraries, so they're directories containing at least PVS files. They may contain other stuff. PVS doesn't care, it just ignores anything that isn't for it, so it's not, it doesn't care about that stuff. By the way, if you use PVS through the Emacs interface, it doesn't really get in the way of anything else you do in Emacs. It's not like taking over your Emacs. For instance, I developed these slides in a PVS session, just because that way I could try out some of the code and do that sort of thing while developing the slides. And you can define your own strategies in PVS, and NASA makes heavy use of that. They've defined many, many strategies in PVS. There is a kind of mechanism in PVS where you can essentially, all the strategies get rewritten down to the core 17 core proof strategies, rules, Shankar calls them, that are the kernel of the proof system in that sense. So you don't have to rely on these being sound in any sense. You can always rerun and say, skip all that, get it down, because all of those have to eventually get down to the primitive rules. So after type checking, it creates a PVS bin file. This is where it can reload the stuff rather than retype checking it. And there's a .pvs context file that keeps track of the write dates and whatnot. So it'll know that, oh, you've changed the file since the bin file was changed, so I need to retype check anyway. It also keeps track of the status of the formulas there. And again, it'll check if the dates are right, and if they're not wrong, then it'll say, oh, okay, generally it'll say they're unchecked at that point. Means at one point they were true, but we need to check it again. So mostly what the prover directly produces as files are the PVS files. Most of the rest is, and PVS strategies actually, but most of the rest the system generates for you. You don't generate a .prf file usually. Sometimes you might want to edit it or look at it, but it's not something you actually play with. A single PVS file can contain multiple modules. Prelude, which is preloaded into PVS, and unlike Hall Light, there is a Lisp image generated, so when you start up PVS, it starts up rather quickly, and it already has all those theories, 152 theories preloaded for you. And there's lots of those. So theories may be parameterized with types and constants. The bodies consists generally of declarations and importings. There's other things like judgments and conversions and things like that. Theories may import other theories, although you're not allowed to be cyclic in that. And importings may instantiate the formal parameters. You don't have to, but at some point it has to be instantiated. But you can be lazy about it, in effect. And importings may instantiate, and they may also map uninterpreted types and constants. This is theory interpretation, we call it. That amounts to the squiggle lines in your STEC presentation. So let's see what else. Okay, so importing, it allows you to reference declarations of other things. Importing a theory implicitly imports all the theories that imports. So this C theory here can talk about the A type if it wants to, because it's through B, it's gotten at A. And this shows, so that shows a type parameter and a constant parameter in the top ATH. So that the square brackets there holds the formal parameters. And then it defines a type and a constant in the body. Then B imports A and gives an int as a type for T and 0 as an element of that type. And C imports B theory, but now it's giving a mapping and saying B is going to be bool and little b is going to be true.
Oh, so what happened to capital T? Like it's unused in the body?
Well, it's implicitly instantiated right there.
But so in the first one, it's instantiated with capital A.
So this is importing BTH, right?
I'm just looking at the first one, at the ATH.
Oh, ATH, T is just within the body of ATH. You can reference the type and the constant. I don't here reference them, but you could reference those. And then when you instantiate them, you're actually getting the instantiations throughout the body of the theory.
Do you need to instantiate them?
No. And often you'll often create another theory that has essentially parallel formals, and then all you're doing is instantiating with these formals, and you just kind of carry the formals along.
Can you use a theorem from a theory with parameters that you just instantiate on the spot?
Yeah. In fact, you can have, like it has constants there. You can have a parameter that's n:nat, and so that's a parameter. We do this with bit vectors, for instance. It's a n-length bit vector. You can then, within a for all n:nat, you can say square bracket n, b vector of square bracket n. So, in some sense, you can't really expand these theories in place, which you would think, with the importing, you can think of it as expanding in place. But that's not the only way you can use it, so.
It sounds like a dependent type.
Oh, in some sense it is, but it's types depending on expressions is what's really going on in PVS. Because we have subtyping, you have types dependent on expressions, but not types depending on types. Any other questions about this slide? This is one of the simpler ones. Theory parameters can also include subtypes, so that's what the S type from T is. It's saying that S is a subtype of T, but we're not going to say which subtype because we don't actually know. And this is from the prelude, actually. So extend is a theory in the prelude, and then we define two variables, and then we say that a function f is extended with the value it becomes a lambda term technically underneath, but basically it's saying that if the predicate on S holds of T, then take f of T, otherwise take the default value, whatever that is for the range. So this, you could put int for T, nat for S, and then you could say D is going to be 0. And that means if it's not defined on if it's only not defined on the nats, if your function from nat to nat is not defined on the nats, then pick 0 as the value. And what happens is when you instantiate the T and S from outside, essentially that S spread that you see there is kind of like an extra hidden parameter. And it gets instantiated. So for instance, if I instantiated that with int and T and, let's see, int, nat, some R type, that one isn't very important, and some element of the R type, then it would basically substitute this lambda for that S pred. So the system knows what the predicate relation between two types is, assuming that it will generate either errors if T and S are disjoint types, or a warning if they're not known to be in the subtype relation. Actually,
So this from is a particular keyword for denoting the subtyping relation.
yeah, type from, you can view that as a single keyword in some sense.
But do you have other type modifiers like this?
Not quite like this, but we do have other type constructors, because we have,
constructors.
right,
Okay.
you know, tuple types and co-tuple types and all the usual stuff. So for instance here, this explains. So if you instantiate it with that, and here I'm saying the range is bool and the default value is Paul, then that's what the S spread will be instantiated to. There is actually a kind of interesting thing. This is not a very good conversion, because there's no easy way to tell what the default range should be, right? The default value for range. But just like in the Hall light, in PVS, it's all subsets are predicates, right? They're the same thing, essentially. And if the range is bool, then false is actually a good value. Because it basically is saying that, if I have a set of natural numbers, that is a set of integers where it's false everywhere that it's not a natural number. And that will kick in automatically. Now, PVS doesn't do covariance or contravariance. The domains have to actually match. And this extend and the restrict are the ways that it's not so bad in PVS, because they kick in automatically as conversions where needed. So in practice, it's actually rarely much of a problem that it has to match the domains instead of being contra or covariant. So you can import library theories. You use the syntax lib at whatever theory instance you want. So that theory instance can include the actual parameters and a mapping if you want to give the full thing. It can be quite complicated there, that theory instance, but that's how you reference a library. You can set the PVS library path. The name is like LD library path if you know Linux at all. And you would set this, for instance, if you install nasalib, you would set this library path to point to the top level of nasalib, and underneath there are a whole bunch of directories, like complex and algebra and things like that. And then you could just refer to them as algebra at thinst, at whatever instance you want. Otherwise, you can create a library declaration and point to a directory, basically. The advantage of the PVS library path is that it's much more portable, because you could install nasalib in one place, I install it someplace else, but who cares? You're just looking for it through the path, through that environment variable rather than any absolute directory. That's about it for that one. You can import with multiple instances, the same theory with multiple instances. There's nothing saying, I've imported it already, I can't import it again. So like in that earlier example, I could import ATH with int0 and ATH with bool false, both, and it's perfectly okay. Direct reference to A, in that case, would be ambiguous. Although if it's in a context and the type checker can figure it out, it will, generally speaking, figure out the parameters. Except, in this case, it would almost never figure out the parameters because constants it doesn't work for. For types it works fine, but for constants, what constant should it pick? There's just no obvious choice. You can also import generically, meaning no, you're not instantiating, you're just importing THA. And so, for instance, you could do an importing of this and that. And it sounds kind of silly, but what it does is that the system will say, oh, if I can't figure it out, I'll just use int0. It's like a hint that that's my preferred one. And if that doesn't work, either complain or force the user to give the instantiation you want. So it'll try A int0, but you may need to give this as the instance if that's actually what you want. So sometimes you want multiple instances, but it can be tedious to type. So we have this as bool A, for example. So you say importing ATH int 0 as int A and ATH bool false as bool A, and then you can just reference int A dot A, and that would have the same meaning as ATH. And in this case, it's short anyway, you might not bother, but sometimes you get very long parameter lists, and it's much simpler to just reference the abbreviation you gave it than.
Can you write ATH in 0 dot A? Can you write like ATH bracket in 0 dot A?
If you wrote that, then it would zero isn't a type, so it would complain because 0 is not a type.
Or no, like take the whole module, right? ATH in 0 dot A.
Oh yes, you can do that. Yeah, so you can, there's a whole thing about naming, but basically you get if you just wrote A and it's ambiguous, you can write A with the square brackets, or you can write ATH with the square brackets dot A. Both of those are perfectly valid ways to reference it. And actually this isn't, this is, I didn't finish this. This should be dot A right there. No, thanks for. So PVS also allows declaration parameters. Everybody loves monads, so. So the uninterpreted type there has a type parameter in it, and the return has a type parameter. Bind has 2 type parameters, as you'd expect. Now this would be really messy if we tried to do everything at the theory parameter level, because we'd have to break it into separate theories. One theory for each, the T and ret could be in one theory, but then bind would have to be in another theory, and a soak would have to be in yet another theory. And that gets really messy really quickly. And you'll notice the type plus there. What that means is I'm expecting a non-empty type there. Implicitly, it's saying that there's an axiom generated that there's a non-empty type, so you can actually reference that axiom in your in any proofs you do. But it also means that if you instantiate this with a possibly empty type, you'll get a proof obligation saying, prove to me that it's non-empty. PVS is perfectly happy with empty types. There's no problem with empty types.
Why do we even want these to be non-empty?
Here it didn't actually matter, but when I tried to instantiate things, it got in the way. And Shankar and I are working on this. This is actually, in some sense, not finished, mostly because the TCCs aren't yet provable because of some of these issues surrounding this. So at the moment, this is a way of trying to get the right TCCs. Then I'll back off on some of these type pluses till I figure out what should be exactly right for it. But this is relatively new stuff. Mostly because relatively new. Well, I'll show it later because this gets repeated. So declaration instances are like theory instances. So if you want to, so here I'm importing it, and then I'm just saying t int is a type t square bracket int. So I'm just giving the instance there, and the ret int is just now taking that and it equals ret on int again. It's just instantiating locally, essentially, is all that's going on. You can have both theory and formal parameters, you know, theory and declaration parameters. There's no problem with that. And then you'll end up having, you know, the theory level and the declaration level. It is possible that you have an ambiguity, and the type checker, largely speaking, figures that out. If you only have one, but there's two possibilities there, it will try to figure it out, and if it can't, it'll give you an ambiguity error. As I said, so here I'm showing an uninterpreted theory, so there's a type and a constant, and then I'm saying there's an axiom that there's more than one element in that type, and that the cardinality is greater than or equal to is a lemma. Card is defined in the prelude, so it's what you expect, that there exists an n, etc., and an f that's bijective, and etc., etc. And then here I'm doing mappings. I'm mapping t to bool and c to true, and I get an obligation that says, prove to me that that axiom actually holds in this interpretation. So anything that you define as an axiom over uninterpreted things, you're now forced to prove when you interpret things. In your interpretation, you may have to, provide more axioms, and then if you and you can partially interpret. There's nothing wrong with just partially interpreting. And in general, if it's partially interpreted and still has something that hasn't been interpreted yet, it leaves it as an axiom until it gets a full interpretation.
So when you have axiom, like, is it possible to have like axioms that are sort of real axioms and like are extending the strength of the theory, or are axioms always of this kind where they're essentially just assumptions and they'll be discharged later?
They can extend the theory, yes. They're treated as axioms by the system. So,
but like this axiom here is not like extending the theory of PVS in any sense, because it's
not
just
in
a local assumption, right?
Right, yeah, it's local to that theory. And now you could get in trouble if you're writing your own theory and it brings this in, and that's a bad axiom. And we've had people do that where they write down what looks like a fully innocuous axiom, and it turns out that they're proving false implies whatever they want because their axiom wasn't quite stated correctly. So,
but like if you proved false from this, no one would say that's a bug in PVS.
If the axiom was stated in a bad way so that you can prove false for it.
I guess the question could be, do you always work with an hypothetical theory, or can you work directly on some top level?
You're always in some theory. Yeah, you're always in some theory, so you're in some context when you're doing proofs. There's no outside of that.
There's like prelude, prelude could have some axioms, let's say.
It does have axioms, like the reals are axiomatic, not constructed.
And you are always importing preludes?
The prelude is implicitly imported always, so everything in the prelude is available to you. As soon as you start up PVS, those are available to you. So when you write theories, so some I didn't have to pull in something for plus or pull in something for, all that stuff is just there.
Can you list axioms that are...
You can get at them, yes. I forget exactly how, but there's a way to get at the axiom. So this is kind of from the previous system that I worked on called the HDM at SRI, but there's actually a whole bunch of words that kind of mean formula. So there's axiom, postulate, theorem, lemma, conjecture. Okay. They roughly mean the same thing, except axiom and postulate are special in that they're treated as axioms. So what happens is you can prove things in whatever order you want. PVS doesn't care. So I often run something, it generates TCCs, I look at the TCCs and I convince myself those are probably all right. I want to get to the lemma that I'm actually interested in. Nothing forces me to do that. At the end of the day, though, if I want to say, I think I'm done, I point my cursor at the theorem and I say, give me the proof chain analysis of this theorem. And it'll go through all the dependencies and say, oh wait, you didn't prove this TCC yet. So that's how that's kept sound in effect.
But it wouldn't ask you to like prove the existence of reals, for instance, in that situation, right?
It wouldn't, no, the reals are known to be, so the integer, the naturals are known to have 0 in them, and the reals contain the naturals, so of course they're not
Right,
empty.
but you said that there are axioms that say these things, right? So shouldn't they show up in this listing?
It might show up, yeah. Axioms do show up, but they're not tagged as something you need to deal with. But they do show up in the proof chain analysis. Yes, they will show up if the dependency is in there. Yes. There's some things that I'm hesitating only because there's some things that just to keep the noise out of there, it just says, you know, reals are non-empty, don't worry about it, kind of thing. So some things are kind of hardwired into PVS in that way, just to keep the users happy and myself. So yeah, that leads to that type correctness condition. An alternative way to do this is through parameters. So now I'm defining the T and the C in the parameter list. And I'm doing an assuming instead of an axiom, I'm doing an assuming. And the assuming is basically a way of saying, here's what I expect to hold of when you instantiate this is what I expect to be holding. And when you then import it with bool and true, you get exactly the same TCC. Okay, I'm just bringing this up in case we need to go back and forth. So this is exactly the same theory we were looking at before. And this part is not, this is what I was saying I'm still working on because it's generating unprovable TCCs. It type checks in the sense that it finishes. It doesn't break into Lisp or anything, but there's a non-emptiness TCC that is unprovable at the moment, and that's what I'm working on. But what's interesting here is you see that even when I'm mapping uninterpreted types and constants, I can still carry along the declaration parameters onto the left-hand side of the mappings.
How much of this can you write inside of proof? Like this is all, you're writing all of this inside of PVS files?
Most of it you can.
Okay.
You put string quotes around terms that are PVS terms, and you can't write a whole theory, but you can write almost anything within the theory you can write. You can't write a definition, but you could write the equals, A equals B kinds of things very easily, and that's often done. There's a case statement that is heavily used that basically allows you to say, at first treat this as a hypothesis, do 2 branches basically. First is a hypothesis, so I can use it to prove my subgoal. Second one is it's now a subgoal, and you have to prove that it holds. So that kind of thing happens. You can think of that as cut if you're used to that in Jensen systems.
So you can like take just add to your assumption, like add an assumption which is like the take a module and then some theorem inside it and say, I want to use this instantiation.
Right. You have to somewhere have imported it so that that theorem is available. But otherwise, yes, you can reference. And one of the things, if you look in the .prf file, it has the proof script that was done for the proof scripts, because it's multiple proof, that have been done for that formula. But it also, for each of the proof scripts, it has, here's the dependencies, the declarations that were used during that proof, so that PVS can easily find them and look for them. That's separate from the dependencies that come from type checking, and that's kept separately because the type checker has that information. But for the proofs, we need to know what's the local information that was brought in for that proof particularly.
So are there any last words? Because otherwise I'll assume we are already in the question section.
Yeah, I think so.
Are there any more questions? 1 or 2 quick ones? before we go for coffee.
What's the difference between axioms and assuming? They both generate type conditions.
Yes, the assuming is basically on the parameters to the
Oh, right, okay, yeah.
and so when you instantiate those parameters, that's when the assuming kicks in and generates the obligation.
Right.
Then I guess we'll have coffee, which I think is in the